Now let's talk about the instructions related to I/O. So when I was actually teaching this topic, someone has asked me, why do you need I/O at all? The main purpose of CPU is to execute the instructions, and till now we have seen the memory related instructions and then the register related instructions. Why do we need I/O at all? Now just think about it. We have executed a program which was already present in the memory. That is what we are assuming till now. We are getting the instructions from the memory and executing them. Now how do you think that this program has been stored in the memory at the first place? Someone has to put it there, isn't it? It is not like we just imagine it in our brain and it suddenly appears in the memory, right? No, we have to type it and send it onto the memory. So before we run a program, we are supposed to put the program in the memory, and after storing the program in the memory, we have to put the starting address of the program in the program counter, and that is where everything starts, right? So we put the program in the memory, and the starting address of the program will be in the program counter, and we reset that sequence counter. Then sequence counter will start executing or giving out the timing signal T0. Now when we are in T0, automatically we have designed the hardware in such a way that it will go to the program which is pointed by the program counter, get the instruction and store it in the instruction register. And now instruction register is already connected to the instruction decoder. So instruction decoder will look at the opcode and it will give one of the 8 codes, D0 to D7, and depending on what the code it is and what is the timing phase, like whether it is T2 or T3 or T4, the corresponding execution will take place. That is all has been happening. But before everything happens, we are supposed to send the program into the memory, right? So for that we are having various modes. So one mode is we have to type it, isn't it? Let's take the simplest case where we are going to type it, and whenever we stroke the key in the keyboard, 8-bit data will be sent into the CPU. Now how is that done? That is done by the I/O instructions. Now see this. We are assuming actually a most primitive computer, and under that assumptions, let's see how everything is being done. Later we shall see what are the normal techniques which are currently being used in order to perform the I/O. If you understand this part, later it will be easy for me to explain the remaining I/O part. And in detail what happens in I/O, we'll again look at it in the I/O topic at the end. Okay. Now just see this. We have already assumed that we are having a bus. Let us say this is the bus, and then we have ALU, and to the ALU accumulator is connected, right? And I told you that there are two registers. One is input register and the other is output register, right? And ALU is connected to this. Now if you look at this input register is directly connected to ALU. In this sense, input register is only connected to accumulator. If you look at the memory is connected to the bus. Let us say this is the memory is connected to the bus, right? So if you have to send something from the input into the memory, we are supposed to send it through ALU only, right? So from ALU it will go. Are understanding it? From input it will go into this accumulator through ALU, and your accumulator is going to store it into the memory, right? And where will this one get the input from? Not from the bus. It is not connected to the bus. It is connected to some interface, right? Let's call it I/O interface. Okay. And now this particular I/O interface is connected to the keyboard, right? So compared to the speeds of the CPU, we are very slow, which means we provide the input or we type very slowly compared to the speed of the CPU, isn't it? Therefore what this one will do is, whenever you type anything, one more thing, assume that from here to here it is serial. So generally it is serial input. Serial input means even when you type a key in one go, the 8 bits will be transmitted from here to here, one after the other, right? And now this one has to transmit it from here to here parallelly, and then this one has to transmit it from here to here parallelly. Alright, so assume that this is the organization. And similarly, coming to the output, so where are you going to give the output? We are going to give the output to the output device, generally a screen or the printer, right? Output will be connected to the bus like this, which means if you want to send something to the output, you send it from accumulator, and accumulator through the bus, it will go into the output. And where will it be connected? It will be connected to the output device here. Okay, output device or output interface, again the IO interface. Now what about these IO interfaces? We shall look at it later in a detailed manner. Now assume that we are going to talk about programmed IO. Programmed IO means in order to read any word from the outside environment into our memory, that word has to go through our ALU by executing an instruction. If we have to send something into the memory, it has to come through this input register, and then it has to go into this ALU, and again it has to get into the memory, which means everything has to involve our CPU signals, which means for every word that you have to read, you might have to execute few instructions. That is also called as programmed IO, right? And it is not very efficient way. You'll understand why shortly. So what we should do is, our CPU should continuously check if input is available in this register. Why? Because input doesn't come very fast. Input devices are generally slow compared to the speed of the CPU. Whenever input is available, it is supposed to read it through to this and then send it to memory, right? And similarly, whenever it is writing onto the output devices are very slow. So what we should do is, we should send the data to the output register and then wait until the data which is present here is read by the output device. Without the output device reading the present data, you are not supposed to overwrite on that. Therefore again your CPU has to wait. Got it? But then CPU doesn't know how to wait. For that reason, we are going to have two flags. Let us say we have two flags here. They are present as a part of the CPU itself, but I am just writing it outside since we don't have space there. So let us assume that two flags are there. One flag is for input and one flag is for output. Now how do we operate it is, initially let's talk about this input, right? So initially our flag will be 0, and an input device, whenever it writes something onto the input register, it is supposed to make it as 1, right? So whenever this flag is 1, it means that some new input is present in the input device. Then our ALU is going to read it, or our CPU is going to give the control signals in order to read that word. Along with that, after reading it, it is going to make it as 0. Now once it is 0, the device will understand that the word which is present here is read by the ALU, or in fact the CPU, which means this particular register is free and it can again put the word there. Then again it will put a word there and again make it to 1, and we'll read the word and again make it to 0. So that is how flag is going to be useful. So flag is going to be useful just for synchronization purpose here. What is synchronization? Our input device is very slow but the CPU is fast, right? Then how can both of them coordinate? By using the flag. So whatever time our input device may take, let it put the data there. After putting the data there, it has to inform us by saying that it is 1. Got it? And similarly, FGU, this output flag will be 0 initially, right? And what we do is, we will send the data from a accumulator. How do we get the data into accumulator? Either we compute the result, or we are sending some data from memory to accumulator first, and then from accumulator we are sending it to the output register, right? So whatever the case it is, we are sending the data from accumulator to output register in our basic model, right? So in order to send the data from accumulator to output register, we assume that initially this output flag is going to be 0. Okay, now we'll write something onto this output flag, output register, and then we make it as 1. It means that you have written the output there. Now the reading of this data will take some time or more time compared to writing, because the reader is very slow, output devices are slow. Now whenever they finish reading this information and then consuming it, they are supposed to say that yes, your register is free and you can write the next word. So for that reason, that particular device is going to read it and then make it as 0, right? Oh, I think I have just gone wrong here. So initially this will be 1. Initially this will be 1. So this one is initially 0, but this one is initially 1. Okay, initially this one will be 1, and now we write something onto it and we make it 0, and the output device will read it and will make it 1. So therefore 1 means, okay, in case of output flag, 1 means the data has been read. 0 means the data is written. Okay, so let's I thought I confused you here. So we are going to have input flag and output flag. Now what does 1 mean and what does 0 mean when it comes to input flag? So if this is 0, it means that the data is consumed. The data is consumed by ALU or CPU. Okay, if it is 1, so it means that the new data is available. New data is available, right? So what we do is, as long as we see a flag 1, whenever we see a flag 1, we are supposed to read from input register. After reading it, we are supposed to set it to 0, so that the input will be provided by the input device. Got it? So what about the output flag? This output flag can be 0 or 1, and now whenever this output flag is 0, so this means that we have just written it. So whenever it is 1, okay, this means that we have just written something. We have just written something onto the output flag, and whenever it is 1, it means that it is consumed by output device. Okay, so assume that this is what we are assuming in order to in our computer. Okay, so just see this. So we are going to have the flag, 1 flag for input register and 1 flag for output register. So whenever the flag is 0, it means that whatever data has come into the input register has been consumed by ALU, and so you can write the next one. Got it? And whenever it is 1, it means that someone has written the data onto the input flag and then they have marked it as 1, so that our CPU will understand that new data is available there. Then our CPU will read it and make it 0. So who will make it 0 in this case? Who will make it 0? This is made to 0 by CPU, right? The reader. And who will make it 1? It will be made 1 by the input device. Got it? Now look at this. In this case, 0, when will output flag, right? So who is going to write onto the output register? Our CPU. So whenever we write something onto the CPU will make it as 0, saying that output is available there, you have to read it, right? So who will make it as 0? CPU, right? And then who will make it as 1? So whenever the data is being read by the output device, after reading it, it should signal the CPU saying that I am done with the register, you can send me the next word. So who will do this? The output device. So remember this. In any case, in both the cases, either after consuming the word, which means after reading the word from input register into accumulator, it is responsibility of CPU to make the flag 0, or in this case, after writing a word from accumulator to the output register, it is responsibility of CPU to make this flag as 0. Got it? So why these flags are used? Just to have the communication, proper communication. Otherwise what happens is, if you don't have these flags, sometimes if you are sending output, then what happens is you might keep on overwriting the same word, assuming that the output has already been read. But output devices are very slow compared to the CPU. CPU will be transmitting the words very fast, and CPU will be overwriting the register very fast. But at the same pace, output register may not be able to read. So we might miss out some of the words. In order to stop that from happening, we are going to have the flags. So we are not going to write anything onto the output unless flag shows 1. And when will flag show 1? Only when the output is read by the output device. Got it? And similarly, in the input also, if you don't have this flag, our CPU might think that a new word has been sent, even though the word present there is old word only, right? For example, a word is being sent there, it read it. Immediately before the input device has sent the next word, it will again read the same word, keep on reading the same word, assuming that it is a new word, right? So now by using the flags, we can avoid that. How we can avoid it is, whenever new data is placed there, immediately this flag will be set to 1 by the input device. Now after reading it, we set it to 0, right? So whenever it is 0, the flag is 0, we can understand that no new input has been written onto the input register, therefore we can wait. So that is how we are going to use these flags for synchronization. Got it? And now if you understood this all, let's go and look at the instructions. Now how can we find out that the instruction is IO instruction? Simple, by looking at the format, right? So we know that our instruction is going to have 16 bits. Assume that the 16 bits are from here LSB 0, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bits, right? These 3 bits are mainly used for the opcode, and this one is used for the mode. The mode followed by opcode followed by operand. But in case of IO devices or IO instructions, we don't have anything called as operand, because we know that there are only 2 registers and flags involved, and we don't need anyone to specify that. The opcode itself is going to say it, and so this complete part is not going to give us any type of address. So we can even use this part also to decide what type of instruction it is, just the same way we used for the register related reference instructions, right? Now let's see this one. We know that if this opcode is giving 111, so if the opcode is giving 111, what will the decoder give us? The instruction decoder, it will give us 7, right? Which means if the condition is D7, right, and along with that if this one is 1, so what is this? It is the actually mode bit in the other instructions, but in this case, if this is 1, it means that it is IO related instructions, and if it is 0, it means that it is the register reference instructions. And that I bit, if it is 1, so this is 7, D7, and I bit if it is 1, and what is the timing signal? T3, right? Then only we are going to go for the instructions, right? So what does it mean? See this, if it is D7 I T3, then it means that we are going for IO instructions. If it is D7 only but I is 0 and T3, it means that we are going to start executing the register reference, right? If it is not D7 and if it is I and if it is T3, then it means that we are talking about the memory reference instructions, and T3 in memory reference instructions, in this case, since I is 1, it means indirect addressing is used, and so this particular clock is actually not executing, but it is computing the effective address, isn't it? If it is D7, sorry, if it is not D7 and if it is not I and if it is T3, it is stall. Stall means it is memory related instruction and it is a direct address given and it is T3, and so we need not compute the address effective address which is already present in AR. AR already contains the effective address. Got it? So by using this circuit, right? So see this. Now if you are having this AND gate, if you give D7, this one, D7 I T3, right, and to the other AND gate if you give D7 I complement T3, to the other AND gate if you give this condition, to the other AND gate if you give this condition, then exactly one of them is going to be 1, isn't it? And depending on which one is 1, that particular circuit will be triggered and that particular operation will go on. Understood this? Okay, now we are talking about the IO instructions. In these IO instructions, we have to also understand what type of IO it is. Got it? We have to also understand what type of IO it is. Therefore, we are going to use these bits. So if this bit is 1, if the 11th bit is 1, if the 11th bit is 1 and if all the remaining are zeros, it means that we are talking about instruction input, INP. Got it? So let's say this bit is represented by B11 and this bit is represented by B10, this bit is represented by B9, B8, B7, B6, right? So in order to identify that it is input instruction, what are the things that has to happen? First one is D7IT3. This has to happen for all the instructions, isn't it? Because we have to identify that it is D7I. So D7I indicates that it is IO instruction, and T3 means we have reached the execution phase. And now which instruction among these that is given by this bit? So which is B11, right? And similarly the next one, it has to also have D7IT3 along with that B10. Now next one is D7IT3 along with that B9, D7IT3 along with that B8, D7IT3 along with that B7, D7IT3 along with that B6, which means we are going to have these many AND gates for each one of them. So we are going to have one AND gate for each one, right? So earlier we have seen this, right? This AND gate is going to be given to one more AND gate, and if this one is having B11, if this one says 1, what does it mean? This is D7, this is I, and this is T3. This entire thing means that the condition which has now met is D7 T3 I followed by B11. So this condition, this one represents that it is INP, input. Got it? So these are the logic functions which are used to implement the control logic here. Got it? So once the control logic is implemented, now I'll show you what are the actions exactly going to take place here. I hope you understood everything right here. So let's see the actions that are going to take place one by one. First action. This one means that we have to read the input. So when will you read the input? We have to test the flag, then only we have to read the input. Now assume that we have already tested the flag, and from the flag we have found out that it is 1, which means there is a new data available for input. Now we can use this condition, right? So input means we have to read from the input register INPR into accumulator. This is the meaning of it. So what is it? INP means read the input from input register. From input register we are reading into AC, accumulator. And what about the testing the flag? We are assuming that the flag has already been tested. And now look at the output. So the output means we have to, okay, one more thing. Here we have to perform two actions. So one action is this one. So whenever this condition is met, we are performing this action. Along with that, I have to even make the flag 0, isn't it? After reading the word, we are supposed to, and the flag in this case is FL, I think FGI. FGI is the name we are using. So this flag represents input flag. We are going to make it as 0, right? And what about this one, next one, output? So what does output mean? from the accumulator we have to move the data into output register, so that output device is going to use that either for printing or for displaying. And even after doing this, we are supposed to make output flag 0. I told you. So whatever the action is, either you are moving the data from input to AC or from AC to output, it is the responsibility of the CPU to generate the signals to make the flag 0. Got it? Now I just told you that before doing either input or output, we are supposed to check the flag, and only then we are supposed to take the action, isn't it? But then we didn't check the flag. So for that reason, these two instructions are not directly issued. These instructions are coupled with these instructions, right? So SKI means skip if input register is 0. So it means that it will check like this: if FGI is equal to 1, which means if input flag is equal to 1, then we are going to skip the next instruction. Now how to skip the next instruction? PC has to be incremented, right? So why is this instruction useful is, see this, if FGI is equal to 1, so what does it mean? If the new input is available in the input register, then you are supposed to skip the next instruction. Generally, the next instruction will be a branch which will be testing the same flag. So what happens is, you will be writing a program, and that program will be testing the flag again and again. As long as it is 0, it will go and test it, it will go and test it, it will go and test it, right? So whenever this is 1, it will stop testing and read the word. Are you getting this? If this is the input flag, what happens is, as long as new data is not available, the value of this input flag will always be 0, right? So whenever the input device writes something in the input register, this value will be made 1. So our CPU will write the code in such a way that as long as it is 0, it will keep on testing it, right? And whenever it sees that it is 1, it will break that loop and come out. In order to execute it, we are going to use this instruction. So how is this instruction going to be useful is, check this. Let us say at line number 100, we are writing SKI, which means skip if input flag is equal to 1. Skip the next instruction. Now the next instruction will be at 101, unconditional branch, okay, to 100. So in case if I equal to 0, then what happens? If I equal to 0, it will not skip, right? Then it will come to 101. See, if you are executing 100 instruction, in case if the flag is equal to 0, it will not skip, it will again go back to 100, and again it will test it, and if it is again 0, it will not skip, it will come here and go back. So as long as it is 0, it will check this, come here, check this, come here, it will keep on happening. And whenever the input flag is 1, it will skip the next instruction. How will it skip it? Because we are doing PC equal to PC plus 1, and once it is skipped, then we are going to the next instruction 102. You tell me what should be the instruction written there. Now flag is 1 indicates that input data is available, we are supposed to read it, isn't it? Therefore INP is enough. Got it? So even though INP, I have already shown you that it is taking only these two parts, micro operations, without testing. Testing is done by this condition. I hope you understood this, right? So why do we use this skip is just to break the loop. Whenever we are going to test something, or whenever we have to wait, then we are going to wait. I think obviously now you understood why programmed IO is not efficient. What do I mean by programmed IO? Writing the program in order to perform the input output is programmed IO. Now by writing this program, what happens? As long as input is not available, we are continuously busy waiting, right? And this is going to be waste of time, because our CPU would have done something useful, but still we are doing this. Instead of that, we could use something else. Later we shall see, using interrupts, how we can avoid this problem. Okay, I hope you understood this. Now what is this skip doing? If fgi equal to 0, as long as if it is as long as it is 0, it is going to go back, otherwise it is going to skip. And generally the instruction that it is going to skip is nothing but the unconditional branch instruction, which takes back to the same instruction. Got it? And next one is skip output, skip SKO. So it will also skip the next instruction in case if this is 1. So now you can assume, you can just think about where are we going to make use of this. Now I told you that when you are writing something to the output register, you are not supposed to write it very fast. You have to give the time for the output device to read whatever you have written there. Okay, so what we do is, first we write something there and then we make it 0, right? So say this, we write something onto the output register. Let us say this is the output register. We have written something onto the output register, and at the same time we made it 0, right? Output flag as 0. Now after this particular device has read this data completely, then only this one is going to be made 1. And so till you make it as 1, you are not supposed to overwrite anything on that. So as long as it is 0, our CPU is not supposed to do any output operation. So that is why, again, you can think of it like this. You are going to write something like this, skip O. It means that as long as it is 0, you are supposed to go back to the same instruction, and whenever it is 1, you can skip this one and go to 102. And what will 102 do? Since this flag is 1, you are supposed to write a new word onto the output flag. That is why I am using OUT. Got it? So see this, even though I have shown you OUT without testing the flag, testing the flag will take place by using this particular condition or this particular instruction. Got it? So again, you can understand that this is a waste of time, because as long as CPU, this particular output device is reading this register one by one, bit by bit, generally this channel, you can assume that it is a serial channel or very slow channel. Then what happens is, till that time our CPU is not doing anything. What will be the other better way? Other better way will be, you just drop some data on that and don't be in this loop. You continue with the next instruction, and whenever data is available here, let it interrupt you. That is using interrupts, that we shall see later. So compared to this programmed IO, interrupt IO is better. Okay. Now see this one. Next one is ION and IOF. So ION means interrupt on and interrupt off. So let us say we have one more flag called INT. So by making ION, we are letting someone interrupt us. ION. And by making interrupt IO off, we are setting the flag as 0, which means as long as interrupt flag is 1, anyone can interrupt the normal flow of the program. As long as interrupt is 0, no one can interrupt the normal flow of the program. So why is it useful is, as a normal user, you might have to be interrupted if your time is over to run the program. If you are an operating system, if you are running in the super user mode, then operating system should never be interrupted. Therefore, while entering into the operating system, that first instruction that you had to execute is make the interrupts, disable the interrupts, and while coming to the user mode, you have to enable the interrupts. Generally, interrupt control is never given to the user in most of the computers, but in our basic computer, let us assume that this is also an instruction using which you can set the interrupts on and off. Okay, anyway, all these instructions, they are just done in one clock, so which means T3 is enough. Similar to the register related instructions, IO can also be performed in one clock, unlike the memory related instructions. Therefore, here the total number of clocks required is 4, and after this in the same one, I didn't add one instruction, so at the end of all this you have to do one more micro operation. Can you guess what it is? For all the instructions, at the same clock T3, at the same timing signal T3, I am supposed to do one more thing. Can you just think what it is? If the instruction is going to be over in T3, the next clock should be, timing signal should be T0, isn't it? In order to get that T0, you are supposed to make it as 0. So after all this, you have to write SC. To SC, you should send 0. Right? So you have to add that to all. Even in the register reference instructions also, after the end of the micro operations, whichever I have shown, you have to add SC to 0, right? So because the sequence counter has to be made 0, so that the next clock which will be generated, the next timing signal will be T0, and so the next instruction will be fetched. Got it? So you have to make it all. And now let's talk about how the interrupts are being used. Okay.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So, first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into university is better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities, but whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is, we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.